for lectures. And in addition to that, I also have there quite a long list of references. I'm going to try to keep these lectures at the level which I hope is accessible to people who may not be in the calculus of variations per se. So don't expect to see very technical and deep proofs, because I don't think that's the place to do that. However, not only the references I provided go deep into the subject, but also, of course, feel free to contact me anytime and ask me for more references on a particular topic or a particular subject that I cover, and I'll be happy to do it. Okay, so so basically what we're going to do here is to study, and can you see well my writing? Is that okay?
Yes.
So we are going to study variational models for phase transitions. And underlying this study will be a notion of convergence of energies, which we are going to go quite thoroughly through that notion, which is called gamma convergence. But before I go there, what unifies the models that I'm going to talk about are basically two items. So what unifies these models first, in the variational context, you'll deal with energies of different dimensionality. So there will be volume, which we call bulk energies. There will be surface energies, etc. Right? And so you're going to have a competition of energies of different dimension. So if you are in R3, you would have, say, the Lebesgue measure in R3, which is, of course, volume. But then you would also have, say, surface. So basically what we call H2, right? The Hausdorff measure of dimension 2. And the other thing is that the underlying maps have discontinuities. So in the language, say, of Sobolev theory, you're going to be outside Sobolev space's context, because you're going to deal with really big discontinuities in the fields that you deal with. Think about fracture, for example. Okay, so the bottom line here is that you have an energy, and we are going to take the approach that equilibria in the quasi-static case, so no time dependence. So in the quasi-static state, fields like to minimize energy. Okay, so that's what we understand as equilibrium states. Okay, everything I'm going to do is going to be at the quasi-static level, so there will be no time dependence during these 5 lectures. But of course, you can use these energies to then think about phase field models, which usually lead you to some parabolic systems. And of course, is a wealth of research on that topic, but that's not what I'm going to talk about here today. So today at the next 4 lectures. There will be no time dependence. Okay, so let's start with the cartoon. And let's assume that you have a container omega. And I'm going to give you 2 fluids. And I'm going to represent the 2 fluids by being, say, one is 0, the other one is 1. So the distribution is going to be given by a function u that takes values 0 and 1, right? So if you wish, you're going to have patches of zeros, okay? And then you're going to have patches of ones. Well, actually, in this case, say the matrix would be ones, right? So that's the remaining of these would be just ones here. So this would be the fluid 1, okay? And normally, okay, so I'm not being very precise here, but that's not the point. And so these would be ones, okay? And the point is that I will also give you, so you can think of this as, this is fluid 0, and this will be fluid 1. And I will give you the total volume fraction of, so normally you have given the average over omega of u, which I'm going to call m. Okay, so that's the volume fraction of one fluid versus the other. This is given. By the way, this is the usual sign for average, which is just 1 over the measure of omega times the integral of omega, right? That's how I define this. And by the way, unless I say otherwise, this stands for the Lebesgue measure of omega, right? So this is just the n-dimensional measure of omega, n-dimensional Lebesgue measure. Okay, so basically what I'm saying is this, I'm going to give you a fixed amount of fluid 0 and a fixed amount of fluid 1, and I'm going to tell you, okay, at the end of the day, I want to fill my container with these 2 fluids, and energetically, what is the best way to do that? You can even think of this as an optimal design problem. So energetically, what is the best way to arrange these 2 fluids? And by the way, don't hesitate to interrupt me, okay? If I go too fast or if I'm not being clear, just let me know. Okay, so I'm talking energetically, so that means that I must have some energy in the background, and I do. And normally the energy is given, so let me call E of u, that's energy of u. It's given by the integral over the container of a function of the distribution u, and W is going to be energy density, so goes from, okay, and by the way, you can do this, here I'm taking 0 and 1 to be scalars, they could be vectors, okay? But I'm going to try, maybe eventually I'll go into vectors. But right now, let's assume that U is scalar valued. And so you go from Rn into R, okay? So here I'm going to consider U's that go from omega into R. W is going to go from R into 0 plus infinity. It's an energy density, so it's non-negative, right? So this is what we call an energy density. Right? And the way that it depicts the fact that we have these 2 phases which are preferred is by saying that, okay, so I'm going to take W to be a double well potential. And it's going to look like two wells, one at 0 and one at 1. That's a typical W. And you can see that obviously, if I do that, then the energy E will be minimized. E is minimized if and only if, of course, W of U is 0 almost everywhere, which is equivalent to saying that U takes the values 0 and 1 almost everywhere, right? It should be at the bottom of the wells. And normally, and the M that I give you is going to be somewhere in between, so that I know that I cannot have just zeros or just ones, because if I want that the average of my fields U will be M, I'll need to have a mixture of the two. I need to have the two phases present, right? It cannot be all zeros or it cannot be all ones, because I'm fixing the volume fraction somewhere in the spinor region. Okay, right. So again, M here, which is the mass, if you wish, is going to be, so it's going to live between 0 and 1, so that I cannot have pure phases. Okay, a prototype that it's used very often for W is W equal to U squared 1 minus U squared. That's a typical one that you'll see in papers and in simulations and stuff. That's a usual one, but it doesn't matter. For what I'm going to say, it doesn't matter the exact form of W. Eventually, I'm going to have to ask my energy to have some properties like growth at infinity, etc. But continuity, I should say that my W is continuous. But that's basically, and with 2 zeros, okay? Okay, now, so if I say that, let me call, say this, here I'm going to call like, so I'm going to take, so if I say it's a subset of omega, I'm going to define U sub A to be the function which is 1 if X belongs to A and 0 if X is outside A. So you're looking at a geometry like this one, right? It's just ones and zeros. Okay, so in this case, A would be the green region. Now it's easy to see that if I want M to be the average of U of A, this is going to be just the measure of A divided by the measure of omega. So this fixes that the measure of A better be M times the measure of omega, right? Okay. So the bottom line is that for any, well, let's say measurable, right? A measurable with the measure of A given by M measure of omega, so that it's admissible, then you'll see that U sub A minimizes the energy because it's just 0. You cannot go below 0. It's the best you can possibly do, right? So bottom line, you have a lot of non-uniqueness in this problem. And one way to resolve that non-uniqueness is to go back to van der Waals, or if you wish, to the Cahn-Hilliard theory of phase transitions. And why is this called phase transitions? Well, because we think of patches of zero as one phase and patches of green, it's the other phase. And there's a transition between the two phases, right? I mean, across these walls, you have a transition from one phase to the other. So that's a phase transition. Okay, and what this amounts to do is this. It says, well, okay, so we have a huge non-uniqueness because I could have, okay, again, I could have like this geometry where I have, let's see, if I want to be consistent, reds were zeros. Okay, so I could have like a lot of zeros here, and zeros and zeros. But then I could have, for example, okay, assuming that this has the right volume fraction, but I could have, for example, a geometry where I want to say have just one blob here, provided it has the right volume fraction, right? So you have a lot of different geometries that will do the job for you. And what this theory does, this Cahn-Hilliard says, you know what? Jumping too often from one phase to the other is probably not a good idea. You're going to pay a lot in surface energy. So maybe what you need to do is to add a small perturbation to that original energy and say, look, you know, okay, so while this is what you can consider these as sharp interfaces, right? Let's smooth them out. So let's assume that now you have diffuse interfaces. So your underlying fields are now going to be continuous, and are going to jump from 0 to 1 across a thin layer around those boundaries, right? And then you're going to penalize every time you go from a 0 to a 1. So what you're doing here is schematically, if you wish, is that so U is 0 here, is 1 there. But now you're going to take, it's going to do that in a smooth way, right? Across a wall, say, of width epsilon, right? So it's smooth, it's continuous. And so that leads me now to a family of energies, which I'm going to call E epsilon of U. So now I'm assuming U to be actually better than continuous. It should be H1, should be Sobolev, should be, I don't know, if that's not familiar to you, think about C1 function, right? Continuous with the continuous derivative, which is not the graph. I mean, the one I have, it's Lipschitz. But okay, something, if you want round the corners, that's fine. And so what I'm going to do here is say, okay, I'm going to keep the same original energy, but I'm going to add a small epsilon square times the grad of U square. Why am I doing that? You see, if U goes from 0 to 1 across the wall of width epsilon, then I know that the gradient of U, it's basically of order 1 over epsilon, right? Okay, so what you have here is something that looks like a 1 over epsilon square, right? And well, that's good news because that means that actually this cancels with that. What's left? What's left is the width of the wall, right? Because gradient U is going to be 0 most of the time here, most of the time there. It's only non-zero here, which is something of order epsilon, right? So that's good, right? Because at the end of the day, I'm just taking my original energy and I'm adding a little epsilon. So it's a small perturbation of the original energy, right? So this is what we call a singular perturbation. Okay, of the original energy. Okay, and by the way, what are we looking for here? We are looking for an energy that it's not too far from the original energy, but it will solve all these non-uniqueness. Hopefully it will give us a criteria that will say, among all these possible designs, there's a preferred one. Okay, now, if you just leave it like this, you won't see much when epsilon goes to 0. Why? Because remember, this one is of order epsilon, but so is this one, right? Because U is 0 here, so W is going to be 0 here. W has two wells, it's 0 at 1. U is 1 there, W has a well there, so it's 0 there. So W is only going to see what happens again here. So it's going to be, again, something of order epsilon. So altogether, this is of order epsilon. And so if you let epsilon go to 0, you see 0. You don't see anything. So that's not good enough. But, and what we want to do, basically, what would we like to do? We would like to say, so let me take U epsilon to be minimizer of E epsilon. Of course, I would have to prove that they exist. And eventually we'll get there. And then what I would like to say is to say, well, look, okay, so somehow in some topology, the U epsilon, so the goal is to show that U epsilons converge to some U, that the U has the good taste of being one of our original ones, exactly two phases, 0 and 1, and U is special. U satisfies some property that singles it out among all these infinite many designs. Okay, that's the goal. Again, as I said, if you just leave it as it is, you don't see much because these energies go to 0. But but it's of order epsilon, which means that if I divide through by epsilon, I get something of order 1, right? So let's do that. Let's take I epsilon to be 1 over epsilon E epsilon. Okay, maybe I should say, let's call it which is now what? It's going to be 1 over epsilon W of U plus now epsilon radius square dx. Now this is of order 1. And the good news is that if U epsilon minimizes E epsilon, it also minimizes this one, right? It's just a rescaled. So I'm not messing up the minimizers at epsilon level, right? Okay, that's good. But now I have something that I can work with. Okay, very good. So actually, this is something we are going to do throughout the course, is to prove that indeed, in some sense, well, first I'm going to prove that these energies admit, which is the same as dealing with this one, admit minimizers. I'm going to prove that in some sense they converge. I'm going to prove that the limit indeed only takes values 0 and 1. And and then what is the criteria that they satisfy. And this goes back to Mort Gerten, who had conjecture that that U0, so U0 only takes value 0 and 1, right? So it's going to be a 1 in some set and a 0 in another set. So let's write, okay, so write U0 as in my notation. I'm going to call U of some set A0, okay? A0 admissible, right? So A0 has the right mass. Okay. And so I think I was using green for the ones, and I was using red for the zeros. So here you're going to have A0, right? And then in the complement, that's where you have zeros. So it's some geometry like this. Actually, it would not be like this, but because it has to be special. But in general, A0 would be something that would look like that. And the point is that was what Mort Gerten conjecture was that, by the way, Mort Gerten was a colleague, well, he's still around here at Carnegie Mellon. And he conjectured that, oh, you know what? So among all these designs that I can have, this A0 minimizes surface area inside omega. So in other words, so you're going to look at, I'm not going to look at the boundaries with the container, but just what happens inside of omega, right? And this is going to be a theorem that says that indeed, among all possible distributions of 0 and 1s, choose the one that minimizes surface area. Now, surface area in the language that we're going to use, it's also written like this. That's perimeter of, say, the phase where U is equal to 0 inside omega, which, by the way, is the same as the perimeter where U is equal to 1 inside omega, right? So that's just the perimeter inside omega. You don't look at the container. Okay. So we have lots of things in our program here. Let me start by proving the following. Oops, I'm not using that color, I'm using yellows. And my claim is that, so assume that you have a sequence, not necessarily of minimizers. So I'm going to call V's, so that I'm going to keep the U epsilons for minimizers and V's are generic, right? So, but assume that you have a sequence V epsilon from omega into R, which are energy bounded. And I'm going to write again what this is. it's this is just integral of 1 over epsilon, W of V epsilon plus epsilon grad V epsilon square dx. So assume that this sequence is uniformly bounded in energy. Assume that I give you one such sequence. Then, so assume this. And
so Irene, that's supposed to be E, right? Instead of I, instead of 1 over.
It's no, sorry. Just this.
Yes.
Yes, absolutely. Yeah. Okay. Or if you want, was 1 over epsilon, E epsilon, right? So, but with I, that's the way it is. If you wish, let me write maybe here. Okay. And so let me start by assuming this and assume further that that the U epsilons have the good taste, that the V epsilons have the good taste of converging to some function V pointwise almost everywhere. So this is just convergence in R. Then I claim that my V indeed only takes values 0 and 1. And that was part of my program, right? Well, this I would have to prove. I have to prove that I have minimizers. I have to prove that my minimizers satisfy uniform bounded energies. But if I prove all that, according to this claim, then I want to show that then I claim that my V indeed only takes values 0 and 1. Okay, so why is that? Actually, to prove this, I don't need to use the whole energy. I'm just going to use this bit here, right? So I know that this is finite, right? So in particular, multiply by epsilon, let epsilon go to 0. So that tells me that the limit as epsilon goes to 0 is 0, correct? Multiply through by 0, let the epsilon go to 0. Well, by epsilon, let epsilon go to 0. Okay. Okay. Okay, so that's fine. And now there is a lemma that most of you, of course, are familiar from measure theory, which is Fatus Lemma. And Fatus Lemma tells you that if you have functions which are non-zero, and if you have pointwise convergence, well, measurable, okay? And if you have pointwise convergence almost everywhere, then the integral of f is below the limiting of the f epsilons. That's Fatus Lemma. Well, actually, you could just put here the limiting of the f epsilons, but suppose you even have a limit, which is what I want to have. Okay, so I had two assumptions. I had this assumption, which I used already. I used part of it. And then I have another assumption, namely pointwise convergence. Well, but remember, I'm assuming W to be continuous. So W is continuous. I'm having that the V epsilons converge to V pointwise. So that tells me that W of V epsilon converges to W of V. This was almost everywhere, almost everywhere. And I have this property here, which I'm going to call star. So I'm going to apply Fatus Lemma to star. Right? In that your F epsons are just W of E epsilon, and your F is just W of V, right? And Fatus Lemma tells me that the integral of W of V, which is F, is below the limitive of the W of V epsilons. Ah, okay. But by star, that was 0. So I'm saying that this integral is 0. W is not negative. So the only way this can be 0 is if the integrand is 0 almost everywhere. But the only way that W can be 0 almost everywhere is if you are at the bottom of the wells, right? Because W is not negative. And that's it, right? So that's a back of the envelope simple computation, which tells you that, if I start with bounded energy and if I have pointwise convergence, then that limit necessarily is one of the sharp interface fields that I started my analysis with, right? So I'm back to the original problem. Okay. And right. So spoilers alert, I'm going to tell you already what's going to happen. And actually, if your original sequence was actually a sequence of minimizers, my U epsilons, as I told you, you'll find a U naught which is special. And actually, what you prove that U naught minimizes energy, but actually, more precisely, so to be precise, so U naught will minimize, well, it will minimize surface energy, but actually, when we go through the analysis, it will minimize, say, a function which I'm going to call I naught of U, which is some sigma times what I told you before, which is the perimeter of the phase U equal to naught in omega. This sometimes is also written, I may use that notation also. This can also be written like this. This is just notation, but sometimes I use one, sometimes I use the other. I'm not too consistent. So actually, there is a constant that's going to come up. In terms of minimization, makes no difference, right? Because minimizing the perimeter or minimizing this is the same, right? It's just a scalar multiplying, right? But eventually, it is going to be interesting because this is it's actually an isotropic surface energy density, in that I can write this as the integral over the boundary inside omega, which is the same as the boundary. I could have also written like this, of sigma times, and I'm going to write here DHN minus 1. So this stands for the n minus 1 dimensional Hausdorff measure which if you are in R3 is just surface measure. If you're on the plane is the curve, it's the length of the curve, and so on, right? So this is just how you measure surface, right? And so you see, writing these or writing these exactly the same, because sigma is going to be a constant. This is going to be a constant in my case. So of course you can bring that out, and then the integral of 1 just times the Hausdorff measure just gives you the surface area, which is exactly the perimeter, right? It's the same, okay? This is just language. But you could have asked me, oh, wait a second. There are many, and by the way, again, spoilers alert, you're going to see that I can calculate this sigma exactly. So sigma is actually going to be given by twice the integral between 0 and 1 of the square root of W of t dt. And we can calculate this exactly. But you could have told me, well, okay, so Irene, let's go back to one of those pictures that you had before. This is the container. Okay, I think I still have 5 minutes. And then say you have one phase, phase A, maybe like that. And you may say, oh, okay, so right now I'm weighting all parts of the boundary in the same way with the same weight sigma, right? But what if I would like to consider what we call anisotropic energies, in other words, energies which depend on the normal, right? So I could have, so I'm going to put here, I'm going to consider a normal nu are the normals to the interface. And maybe I'm looking for getting at the end of the day an isotropic surface energy. Now, right now I'm working with fluids, so U has scalar value that I'm basically just looking at the density. I could be playing this game for solids, which is much more complicated, and it has been done to some extent. But, and then it's important because, say, if you're dealing with an elastic solid, you have crystallography, right? And so these are anisotropic materials, and the behavior does depend on the normal. And so instead of this, you maybe you'd like to get instead, again, you take the boundary of the interface inside omega, the part that's inside omega, and then but I would like now to have a sigma that depends on the normal. Why not, right? That's an isotropic, depends on the normal. Can I do that? And the answer is, actually you can. It's a little bit of reverse engineering, but instead of considering what we call the Dirichlet integral, which is what I have here, right? It's just Dirichlet integral, does not see the orientation, it's just a magnitude, right? I could have a function that is more complicated than that, and so I could have something that looks like this. I could have, for example, 1 over epsilon W of U plus, say, epsilon and now an F of grad U. By the way, and why am I taking power 2? I could take power P with other P's, right? P is equal to 1, it's a different ballgame. But say P bigger than 1 could be done exactly as I'm doing it. It could be this, it could be even more complicated than that. It could be even coupled. Instead of writing this, maybe I could write something, for example, like a 1 over epsilon, and now an F of X U epsilon grad U, for example. And this was actually studied by Guy Bouchité. So you could actually have a coupling of these fields. And indeed, then you get energies which are more complicated and which are going to look more like so. But I think I am at the end of my time. So I'm going to stop here for today.
Thank you very much.
You're welcome.